Hello everyone, this is Mr. Teo again. Right now is week 11. Basically, we are going to continue our module by going into the second order system, which we are going to talk about the uh, damping ratio and the undamped natural frequency, which you have already have some idea during your lab 5 briefing. Now, without further ado, let me go into the slides of the today's lecture.
Let's try to understand what is omega n and what is zeta. You can view zeta as the break to oscillation. When zeta is 0, there is no break to oscillation, hence the whole system will oscillate at its natural frequency. For this case, we set omega n at 2.5.
You can recall what I did in lab 5, or rather using this same simulation. If we set the damping ratio, that means by sliding the scale to 0, and then you set a, let's say, arbitrary undamped natural frequency at 2.5, and then if you click the run, basically it'll give you an oscillating sine wave with no stable steady states value, and this is what we mean by undamped natural frequency. Now, you can view damping ratio as a break to the oscillation. Now, in any feedback system, by nature, it should be able to oscillate if the phase and the magnitude is right. So it will have an oscillation possibility. Now, undamped natural frequency is in the situation whereby the system starts to oscillate and you don't apply any braking or any resistance to this oscillation. So as a result, it oscillates to its fullest, and that's why we mean by having the damping ratio zeta equals to 0. That means that's what we mean by zeta.
As we increase a little bit of zeta, meaning we increase a little bit of break, oscillation will start to decay away. This occurs when zeta is between 0 to 1. We call this underdamp. Note that the roots of the underdamp case is two complex conjugates. It have two roots because it is a second order system.
The damping ratio from 0 to maybe within 0 and 1. So we give it a little bit of break, right? A little bit of break to the extent whereby it is able to finally settle down, right? It starts with oscillation and each peak is getting smaller and smaller, and finally it reaches steady state value. And this range of zeta that is between 0 and 1 is the case whereby we call it the underdamp, right? Underdamp. So that means not really a lot of damping, but it's a little bit of damping. We call it underdamp. And under this situation, if you look at the roots for the denominator of the generic equation, it will look something like that, which is complex with a j term here, right? So therefore, the roots are two complex conjugate. That means one of them is a plus, one of them is a minus. So you have plus j term and minus j term. So this is the situation for the underdamped case. And this case is the situation whereby we study all the timing characteristic, like the maximum peak, like the peak time, rise time, settling time, or steady state error, etc., etc. This is the most interesting stage, whereby a lot of control people would like to put their control system into this stage because it's the fastest, and also at the same time it is able to settle down to a steady state. Okay.
If we increase zeta until it equals to 1, there will be no more oscillation. Instead, the output response will rise slowly to 1. This is what we call critically damp, where the system will have two identical negative roots.
Okay, so proceeding from moving the scale from a zeta between 0 and 1 to a zeta of exactly equals to 1. This is a case where we call it a critically damped. Now, critically damped because this is at a point whereby there is no peaking at all. You will just go up and straight to the settling of the steady state value. Of course, it looked very nice, but of course, if you compare the rise time to the underdamped case, it is slower. The underdamped case probably will rise here much faster, but it settle down in a while time. So therefore, this situation is whereby the denominator of the generic equation has two identical negative roots, which is s equals to minus omega n, right? Of course, this breaking here is slightly bigger with zeta equals to 1. But of course, previously it is zeta between 0 to 1, 0 to less than 1.
If we continue to increase zeta to beyond 1, the system output will rise slower and slower. Hence, time taken to reach the final value will be longer. This is what we call overdamped. The system will have two real and negative roots.
Okay, I'm sorry for this visual here. There is this is zeta omega n plus minus omega n squared zeta minus 1. So I'm trying to replace a symbol here because this is actually the old symbol. The newer symbol is we are going to use the zeta in this sense. Now, if you continue, this is a sidetrack a bit. If you continue to increase zeta greater than 1, this is a situation we call it the overdamp. That means a lot of break. Now you will realize that the actually rise times go up very slowly. Of course, this one will not have oscillation because oscillation may never happen. You just break it to the maximum, right? So of course, under this case, you have two real and negative root. Notice that there's no more J term. In the underdamped case, there's a J term in front, but now for the overdamped case, there is a no J term here, because the square root of this thing is positive, right? So that's what happened to the overdamped situation.
Let's take a look at process dynamic of a second-order system. This process dynamics is mainly for underdamped system whereby zeta is between 0 and 1. We are particularly interested in underdamped because it is the fastest and oscillation will damp away eventually. Details will be looked into when designing a system in underdamped condition. Parameters such as maximum peak, settling time, rise time, delay time, peak time, etc.
Okay, so this is exactly what I have just mentioned. Out of course, the undamped case will never be of interest to most of the people designing the control system because it's oscillating. It never settled down to the final value K. So this is left with the three situations whereby it is underdamped, critically damped, or overdamped. Now, of the three, this is of the most interest to most of the people that do the control system. Why? Because it is the fastest in terms of rise time, and also at the same time, it can settle down to its final value, which I have just mentioned before. And because of all these things, because of this fast rise time, we got to characterize the maximum peak, the delay time, the rise time, the peak time, and the settling time carefully so that you won't have a system that turn from a normal that means a stable system into an oscillatory system, because there is a tendency, or if you are not careful, you might turn it into an oscillatory system even though it's faster, right? So these are the key few key parameters we always look at. First of all, the maximum peak. The maximum peak is a measure from the overshoot of the one, how high it overshoot. And let's say, for example, it goes up to 1.4, then 1.4 minus by 1 will be 0.4 out of the total. 0.4 divided by 1 is about 40%, right? So this maximum peak will be 40%. That's one example of maximum peak. Now, delay time will be the time taken for the output signal to rise all the way up to 50% of the final value. The final value, the final desired value will be 1, right? So therefore, 50% will be 0.5 volt, right? So if you hit 0.5 volt, you check the time taken from 0 to this point here will be what we call the T delay, the delay time, right? And that's one of them. Now, there's one we call the rise time. The rise time, of course, in the formula sheet in the form, you realize that there is 10% to 90%, and there's another one from 0% to 100%. Now, this one I'm trying to indicate is 10% to 90%, and so this is if the signal rise from 0.1 to 0.9, that is your rise time. Okay. And then, of course, for the T-peak, it will be the time taken for the signal to move from 0 to the peak, right? and this is the PT peak time, right? And lastly, last but not least, is the settling time. Is the time taken for the signal to settle down within a band of tolerance, right? So for example, if I say the band of tolerance is plus minus 2%, 2% means 0.02, right? So plus minus 0.02 means that 1 minus by 0.02, it will be 0.98, right? And 1 plus 0.02 is 1.02. Also within 0.98 and 1.02, if the signal go in and never come out, the first entry will be the point whereby it is called the settling time. Now, you see, up to here, it never come out, right? So this first entry will be taken as the time that it's settled within that band, right? And so this is your settling time. Of course, if you have a 5% criteria, then it will be ranging from 0.05 to 1.05, right? So that's the difference between the banding, right? Of course, with this, all these parameter, MP, TD, TR, TP, TS, and of course, the settling time, all these can be calculated so long as you are able to find the omega, n, and zeta. That means the undamped natural frequency and the damping ratio. If you can find these two, all you need to do is just go to the formula sheet and look at each of the term, and you substitute in, you'll be able to calculate each of these parameters. It's very straightforward. Right?
Once we know the value for zeta and omega n for an underdamped system, each of the timing parameters can be calculated using the formula in the formula sheet.
As I have mentioned just, once you are able to determine these two guys, omega n, which is the undamped natural frequency, and zeta, which is the damping ratio, you will be able to, from the formula sheet, calculate each of these terms. For example, T settling, it is in terms of zeta and omega n, for whether it's 2% criteria or 5% criteria, right? The 2% band or 5% band. Now, for maximum peak, again, is only dependent on zeta. And then if you, whether you want absolute value or you want in terms of percentage, both of them are only dependent on the zeta value, right? For the delay time, again, is dependent on the zeta and omega n. So if you have both of them, you'll be able to calculate TD. Now, rise time, again, same thing, is pi minus, pi is 3.142, so it is a constant. Beta is given by cos inverse of zeta. So as long as no zeta, you would know beta, right? Omega d is given by omega n squared root of 1 minus zeta. So you know omega n and zeta, you will be able to solve omega d. So therefore, this thing with omega n and zeta, you will be able to solve, whether it's 0 to 10%, 100% or 10% to 90%. Now, TPIC, similarly, as long as you know omega n and zeta, you will be able to solve the TPIC. So that concludes why these two parameters of omega n and zeta is so important for the second order system, second order underdamped system.
Please go through e-tutorial 9.
Now, we are going to go through quite a number of questions this week, which is namely question 2, question 3, question 13, 11, 12, and 14. Same thing, for every week, we will use the blackboard instead of, but of course, there is already a video that is being recorded in the tutorial session. If you were to go to the tutorial site, you would be able to see it. Let me just briefly share the blackboard. Maybe I should stop sharing first. Stop sharing first. Then I go to the blackboard. Tutorial. Now you can see that, let me share. For example, this week of week 11, right? So you can see that there is a video recording for e-tutorial 11. So if let's say you miss my description or what on the e-tutorial, there will be another video recording for the e-tutorial done by Ms. Shirley Go. And basically you can use this to understand the explanation. So if let's say you find my explanation is not clear, you can use this. So each of the tutorial session will also, the same question that we discussed will be also appended here for each of the weeks. Okay, so now let me go to the whiteboard. Let me go to the whiteboard, and of course we will first start with the first tutorial question, right? So what is the first tutorial question? Okay, give me a while. Okay, this is the whiteboard. Let me go to the first tutorial question, which is what we are going to discuss here. First of all, we will be discussing question 2. Sketch the. Okay, so for question 2, it's quite a straightforward question. Actually, we don't need a blackboard here. Let's share the solution directly. So question 2, it says that sketch the and label the first order response. So first order response, as we know, first order curve is like that with a step input. If you have a step input, then your output response will basically go up like that. Now the key parameters for first order system you need to identify is basically the time constant, which is from 0 to 63%. This is the time constant, right? The time constant here from 0 to 63%. So this is the time constant, and the settling time will be TS, right? TS, which is from 0 to 5 tau. That means 1, 2, 3, 4, 5. 5 times the time constant, right? And of course, the steady state value as well, right? So these are the few key things of the first order response. So as long as you label these few things, then basically this is what is required for the first order system for question 2. Now the next question will be, let's take a look. Let me take a look first. The next question will be question 3. Question 3 is also on sketching. So let me just flip to question 3. Now it says that sketch the second order step response, label and define the key parameters of second order response. So basically, second order response, we are referring to the underdamped situation, right? Whereby the zeta is between 1 and 0, right? So this will be the response curve. Now the key parameters basically will be maximum peak, T delay, okay, T rise, T peak, and T settling. Now you should be able to describe what is maximum peak. That means the overshoot of the 1, and that is in terms of percentage. If you, for example, just now when I mentioned to you, if this is 1.4, then 1.4, it exceeds the 1 by 0.4. So 0.4 divided by 1 will be 40%, right? So this is a 40% maximum peak. So it's a how many percent overshoot. Of course, maximum peak can be in terms of percentage, or it can be in terms of absolute value, right? Now, also, the T delay will be the point whereby the curve moves from 0 to 50% of its final value. The final value is 1 volt, and then, of course, this will be the time taken for it to move from 0 to 50%. Now, T rise is, again, for the signal to move from 10% to 90% for one case, and then the other case is from 0% to 100% for the other case, right? So this is the rise time situation. Now T peak is the measure of the time for the signal to move from 0 all the way to its maximum peaking. So this is the time taken, right? Now T settling, unlike the first order, which is 5 tau, there is no 5 tau here. It will be the time taken for the signal to settle down, right? To settle down within the band. So let's say the band is a 2% band, so it's plus minus 2%. So plus 2% will be 1.02, minus 2% will be 0.98. So as long as the signal cross into this region of 0.98 to 1.02 and never come out, this first entry point will be your settling time, right? Now, similarly, if it is 5%, it will be 0.05, right? 0.05, then it should, the band, the tolerance band will be starting from 0.95 to 1.05. Now, as long as the signal goes in to the band of 0.95 to 1.05, it will be considered to be within the 5% tolerance, and therefore that will be the settling time for the 5%, right? So that's as simple as that. So this is question 3 solution. Now the next question we are going to discuss will be, okay, for this guy here, question 13. Now question 13 talks about a motor, right? A motor diagram here, which is given by this transfer function, 3 over 2s plus 0.4. And of course, it has a feedback factor, feedback gain of kf, right? So of course, the output is the velocity, the speed of the motor, Vs. Input is just a unit step function, right? Input unit voltage. Now, so the question part 1 asks you to obtain the time constant of the motor without feedback, right? So what is the time constant of the motor without feedback? It means that there is no feedback here. So this one you delete away, the Kf is asking you what is your first order time constant. Now, first order time constant, what do we compare with? Now, let's go to the blackboard for this case. The whiteboard, sorry, not blackboard. So, because so used to blackboard. Now, let me first go by setting up the writing material. Give me a while because I have not hooked up the system yet. Okay. Now I'm plugging in the system. I'm plugging in the system so that I can write it using the whiteboard, right? Now, okay. First of all, what was the equation? So you have a forward block, right? Forward block which is given by 3 over 2s plus 0.4, right? Now it's asking you what is your time constant. Now this is a first order system, right? Agree? Why do I say it's a first order system? First order system because the denominator, the highest power is 1. So this is a first order system. Now with a first order system, what is the generic equation? The general equation that we should be comparing to. The general equation that we should be comparing to will be K over tau s plus 1, right? Remember this? K over tau s plus 1, right? So now, can I compare these two right now? Now, if I look at the denominator first, just look at the denominator because denominator is always the most important, right? So if I try to equate this with that, 3 over 2s plus 0.4. Straight away, if I look at the, let me change the color a bit. I can change. Straight away, if I look at it, straight away I cannot equal because this is 1, this is 0.4, right? So of course 1 cannot equals to 0.4. So I must do something to this 0.4. So in order to change that to 1, I got to divide everything, all the terms by 0.4. So if I divide the top by 0.4 and divide the 2 by 0.4, and I divide the 0.4 by 0.4, what I get is essentially, if I 3 divide by 0.4, what do I get? 3 divided by 0.4, I get 7.5, right? 7.5 on top. And then, of course, 2 divided by 0.4, I get 5 below. 5s, right? Plus by 1. Now, it looks much better, right? Now you have 1 compared to 1, right? Left-hand side and right-hand side now is 1 compared to 1. So with this, can I say that the tau, so the first question is, what is the time constant of the system without feedback, right? So I took out the feedback. Remember, originally there was the feedback here. There was a feedback of Kf over here, right? Kf. I took it out. I break this loop, so there's no more feedback, right? So that's why I arrive at this. So now it asks you what is the system time constant tau. What is tau when there's no feedback? So tau essentially will be equals to, based on this comparison, tau will be 5 seconds. Right? So that's for the first part. Now let's go and look at the second part. Second part, what do they want? Let me move back to the question. Now, second part, they want to obtain the output, the closed loop transfer function of V over U of S, right? Closed loop transfer function. Now, let's go back to the whiteboard again. Now, how to find the closed loop transfer function? Now, they want you to close the loop back. So basically, what happens is, if I if I were to clear this open loop and I close the loop, basically now they want you to calculate for part 2, which is the closing of the loop. So you have to close back the loop, which is a negative feedback here. So you close back the loop. Now they ask you to find V of S over U of S, right? So what is part 2 is, what is V of S over U of S? Now, V of S over U of S is pretty straightforward. Remember, this is a negative feedback, and we use rule 7. Rule 7 states that this must be equals to G of S over 1. Since this is negative, then this side must be positive, right? Multiplied by G of S, H of S. Now, what is your G of S? G of S will be this guy, right? G of S will be 3 over 2S plus 0.4. Right? Same thing for the bottom side, 3 over 2S plus 0.4. Now, H of S, what is it? KF, right? So this is how you determine, right? So H of S, K of S. So what does the, so they want you to express this whole thing, of course, in terms of KF. Let me take a look just to double confirm that we are doing the right thing. Let's go and take a look at the question. Right, so make sure that, okay, let me take a peep at this is question 13, right? Question 13. Okay, so it's in terms of KF. So right now, let's go back to the whiteboard, just in case I get carried away and solve it in another direction. So right now, if we were to rewrite this guy properly, so how to rewrite this guy properly? Now, if we were to rewrite this guy properly, so you have what we call 3 over 2s plus 0.4, right? Divided by 1 plus 3 over 2s plus 0.4, and then you multiply by kf over here, right? So indirectly, you can write it as, right, 3 over 2s plus 0.4 over, so the denominator will be 2s plus 0.4. So you have 2s plus 0.4 divided by 2s plus 0.4. That is also equals to 1. Same thing. Then plus by 3 kf, right? 3 times kf over 2s plus 0.4. Now, since all the denominator are the same, we can actually essentially cancel all the denominator and write down all the numerator. So essentially what we have here is 3 over 2s plus 0.4 plus 3 kf. So your solution is actually normalize everything with 2. So if you divide top and bottom by 2, you got 1.5 on top over s plus by, if this one you divide by 2 will be, you get 0.2, right? Plus by 1.5 kf. So if you look at your tutorial solution, basically it's this value, right? So v of f over k of f is this value, right? So that is part 2 of question what? That is question 13, right? So this is question 13. Question 13, part 2, right? Now what about part 3? Part 3, let me see, part 3, let's go and take a look at the question. So part 3, they ask you to calculate the KF required such that the closed loop time constant is 2 seconds. Now the closed loop time constant, bear in mind, now is the closed loop time constant. So let's look at the equation that we solved so far, and let's share again the whiteboard. Now this is the final equation that we shared just now. So again, it's still basically first order, because the s is still to the power of 1. Now for first order, again, you compare to what? Compare to k tau s plus 1, right? Now, of course, if you compare to k tau s plus 1, this guy here is not 1. This guy here, right? This term here is not 1. So what do? You got to make sure that this term equals to 1. So in order to make this term equals to 1, you got to divide the top and bottom every term by this term here. So if you divide the top by this term, it will be equals to, what? It will be equals to 1.5 divided by 0.2 plus 1.5 kf over 1 over 0.2 plus 1.5 kf s, then plus by 1. Now, so this is more like it. So because you can compare 1 and 1. And of course, now it reveals to you what is your time constant. So for the time constant, if you compare tau with this guy, so essentially your time constant would be, if I'm allowed to write over here, because that side is a bit sensitive, I cannot basically write on it. So if I were to, if I were to move to here, tau will therefore equals to 1 over 0.2 plus 1.5 kf. Right? So this is for part 3. Right? Then, of course, did we actually solve it already? So let's look at the question again before we get carried away. So basically, so did we get it already? So so they say, what is the kf required such that the time constant is 2 seconds? They say the time constant is 2 seconds. So not finished yet. So now back to the whiteboard. Share. Now time constant is 2 seconds, meaning that I got to basically do what? Basically do what? I have to basically equate this guy here. This guy here, right? Can you see? This guy here, I have to put it to 2. Now after I put it to 2 and I solve, then I would have essentially kf equals to some value. Now if you solve it carefully, you would get, with this, you will get kf equals to 0.2. Oh, kf equals to 0.2 by plugging in this guy equals to 2, and you solve for ks, then the kf will be 0.2. So this is for part 3, right? For part 3. Okay, for part 3. So now for part 4. Part 4, what does it ask you for? Part 4, they ask for a part 4. Now part 4, they ask for calculate based on the transfer function in part 2, if kf equals to 2 and input is 1 volt, apply, obtain the unit step function, unit step response, or VT. So basically part 2, what is part 2? Now part 2, let's take a look. Part 2 is basically this guy, right? Which is what we got here, gotten here, right? Which is 1.5 over S plus 0.2 plus 1.5 kf. Now let me rewrite the whole thing into another page. So maybe I can erase the top part here. Maybe I can erase the top part here to have some space to write, because or else I don't have any more space to write. So if I erase the top part here, now let's solve the part 4 over here. So it says that part 4, we have the transfer function v of s over u of s is equals to, we can use either this one or this one. Let's use the top one. So is equals to 3 over 2s plus 0.4 plus a 3kf, right? And what is the condition that they give? Now, condition they give is basically, condition they give is kf is 2, right? And step input is 1 volt. Input step is 1 volt, right? Obtain the unit step response of t. So they will want you to find the unit response of t. Now back to this, okay? With kf equals to 2, so this guy will be equals to 2. You substitute a 2 here. You substitute a 2 here, and if input is 1 over s, right? 1 over s, because you basically are using a unit step function, right? Unit step function. So 1 over s. So they tell you with this, can you calculate what is your VT? Now VT. So before you find VT, you must be able to find VS, right? So what is VS in this case? Now, VS will be equals to VS will be basically equals to 3 over 2s plus 0.4, right? Here, plus by 3 times 2 is 6. Plus 6, right? And multiply by 1 over s, right? Because you bring your 1 over s over here. So essentially what you are getting is 3 over 2s plus 6.4, right? 6.4. Multiplied by 1 over s. So essentially what you are getting is, okay, if you divide throughout by 2, which is going back to just now the case, you have 1.5 on top, and you have s plus a 3.2. And then of course you multiply by your s in, so you got s 1.5 s plus 3.2. Now under this case, how do we find VT? Now in order to find VT, we got to do a Laplace inverse. That means moving from the time domain back to moving from a frequency domain, or rather the s domain, back to your time domain. We got to do a Laplace inverse, right? Laplace inverse, basically you just go to look at the table, right? Table for, let me find the formula sheet first. Okay, formula sheet, and look at the table. Before I share, let me search for it first. It's usually at the last page. Last page of the formula sheet. Okay, I'm there. So let me share so that you all can see. Okay, share. Let me share the Laplace table. Now, if you look at it, just now our expression basically is this form, 1 over s plus a. Now, if you plug in this and then you rewrite it in terms of a, 1 minus e to the power minus at, then you should be able to get the expression for it. So now let's try to substitute in using this equation, right? Now let's go and share. Now, if I take this and I do the Laplace inverse, then basically I can say that v of t should be 1.5. I take out the constant 1.5 and I do the Laplace inverse for 1 over s plus 3.2, right? So essentially it will be 1.5 multiplied by the equation that we saw just now, right? Which is 1 over a. 1 over a, what is a? Is 1 over 3.2, right? A is 3.2. Multiplied by 1 over a multiplied by 1. Let me see. 1 over a multiplied by 1 minus e to the power minus at. Okay, so if I have 1 minus e, 1 minus e to the power minus a is 3.2. and t. So if 1.5 divided by 3.2, so you just simplify it. Basically, this will be a solution for part 4, right? Which is essentially what is being shown, right? So with that, we have some more question that we are going to discuss. Okay, let me share the question again. Share more question. Now, the next question will be how to solve this guy in terms of making it into a closed loop transfer function, meaning that y of s over u of s. Oh, so this one actually is illustrated in the textbook, or rather the main document. But in view of the time, I will drop this first, and I will go on to the next question, because this exactly solving of the steps is inside the detailed lecture notes. So let's continue with the next question, which is question 12. Then there will be one more last question, which is question 14. Right, so we got 2 more questions to go. Now for question 12, they basically give you zeta and omega n and ask you to determine what is maximum power percentage overshoot, the TD, TP, TS for 2%. So this is a very straightforward question. So if you look at the formula sheet again, you scroll to the timing diagram formulas for underdamped case, right? Timing diagram, timing signal, right? Timing signal. So what is PO? So with your zeta, you already know. You just plug in, you get your PO, right? And then the other one is your what? Is your TD, right? What is a TD? So you look at TD and you know your zeta and omega, and you just plug in the value, you will find your TD, right? Then the next one is what's your TP, the peak time. So peak time, again, you know your omega n, you know your zeta, you just plug in, you get your peak time. Oh, that is just mathematical substitution. And what is your settling time of 2%? Now, settling time of 2%, there is 2% criteria and 5% criteria. So you just use a 2%, will be 4 over zeta omega n. So you just plug in your zeta and omega n, you can calculate your settling time. So this is quite a straightforward. I wouldn't be doing the substitution for you, but I will just point to you that that's how you go about doing it. So this is okay. Now let's move to the question. Now question 14. Right? Question 14, they give you a transfer function, right? G of s, which is 10 over s squared plus 6s plus 15. Now they say if a unit feedback is applied, calculate the steady state error. Now, unit feedback, what do you mean by unit feedback? Unit feedback means okay, let's go to the whiteboard. Let's go to the whiteboard and then let's clear it first. Let's clear this guy. Let's clear this guy, and then now let's do the equation. So you have 10 over s squared plus 6s plus 15, right? So your G is actually 10 over s s squared plus 6s plus 6s plus 15, right? There's an s here. So this is your G, right? And they're asking you what is your steady state error if there is a unit step feedback, unit feedback. So unit feedback means that you have a direct feedback like that without any gain function. So this is your h of s. And h of s is actually equals to 1. This is what we call unit feedback. Of course, in terms of feedback for stability, is always negative. So they're asking you what is your this steady state error function. Right? Now error function, we know, as we already know, error function divided by u of s, which is the input. This is, let's say, y of s output, right? Now, for y of s over u of s, we already know that it is G of S over 1 plus G of S H of S. Now this is for using rule 7, right? Rule 7 of your block diagram manipulation for negative feedback, right? So rule 7 is quite straightforward. But for error function, which is this guy here, the equation to memorize is slightly different. It's actually E of S over U of S, right? Instead of Y of S over U of S, it's E of S over U of S, and it is actually equals to 1 over 1 plus G of S H of S. Now, how do you remember this? Now, if you see, in order to get back E of S, I got to move backward, right? Move backward. And this has to be divided by this G of S. So if you take the expression of Y of S, you divide by the G of S, basically you get 1 here, right? You divide away the G of S. So therefore, the error function will be something like that, right? So what was the question again? They asked you to state the steady state error. Now, steady state error, of course, is given by this guy here, but of course, with the multiple. So you have to first find out what is E of S, right? E of S will be U of S. You just bring over the U over up on top. So it's U of S over 1 plus G of S H of S, right? Okay, so in this case, usually it will be a unit step function. This guy will be usually 1 over S, right? Of course, G of S is this term here, and H of S is 1. So if I assume, right, limit of so steady state error is equals to limit, right? You have to take a limit. Steady state error, you have to limit, and of course, when we want a steady state error, usually we have to wait very long, right? Because this is the point where it's settled. So a joke that I always crack, in order for you to get steady with your boyfriend or girlfriend, you got to wait very long. So this is what we mean. The time has to approach infinity. And we know that the time and frequency is inversely related. Right? So if the time go to infinity, what does it mean? The frequency will go to 0. And frequency is related to S. S is actually 2 pi f, right? Is actually S is actually 2 pi f. So therefore, this is actually, if let's say f tends to 0, that means 2 pi f will also tends to 0. That's the reason why we have the limits of S approach to 0, right? So with this, of course, the equation is given by S E of S, right? And then if you plug in the E of S here, you get limit of S approach to 0, S multiplied by your 1 over S on top, right? 1 over S, and divided by 1 over G of S H of S. Now this S and 1 over S cancel each other. So now you are left with what? This guy is 1. So you are left with solving for S approach to 0 when, and then bracket 1 over 1 plus G of S. Right? What is G of S? G of S is this guy, 10 over S squared plus 6S plus 15, right? 10 over S squared plus 6S plus 15. So you just need to plug in this into there. 1 over 1 plus 10 over S squared plus 6S plus 15, right? Now in situation whereby the S term goes to 0 and 6S term goes to, when the S term goes to 0, right? Because we take the limit, so therefore you are left with what? You are left with 1 over 1 plus 10 over 15. So if you solve this, this will be kind of like 15 over 25, right? Which is giving you 0.6 volt. So that is for part 1, the steady state error. So ESS, steady state error, part 1. Right, so this is for question 14, part 1. Question 14, part 1. Right, I leave for a while, so for you all to digest. Then before we go to the next one, right? Let me go to the next one. Of course, you all can play it back. later stage. But let's go to the second part, whereby they say the peak time, then the settling time, then of course the last but not least, the maximum peak overshoot. Now all these require what? Require your computation of require your computation of what? Remember your computation of zeta and omega n, right? So what is your closed loop transfer function right now? So let's go back to your board. Now this where is your closed loop transfer function? Closed loop transfer function will be given by G over 1 plus GH, right? G over 1 plus GH. Then with G over 1 plus GH, if you compare the denominator with your generic equation, then you will be able to find what is zeta omega n. So let's try to do that. So before that, I will just clear the drawing because it's too messy. I will just start a fresh page. Now, for part for question 14, part 2, 3, and 4. So question 13, question 14. Let me write it down. Question 14, part 2, 3, and 4, right? You require to first find what is omega n and zeta, right? Damping ratio. Now, in order to find this, you got to compare two things. You know the generic equation is k over omega n squared over s squared plus 2 zeta omega n s plus omega n squared. This is your generic equation. Generic, right? And then, of course, you have to also find your closed loop transfer function. Now, closed loop transfer function is given by your g of s over 1 plus g of s h of s. Now, h of s we already know is 1. G of s is just now what we know is 10 over s squared plus 6s plus 15, right? So this is 10 over s squared here. Sorry, I cannot write. Squared plus 6s plus 15, right? So similarly for the top. So I need to solve this closed loop transfer function before I can start comparing closed loop transfer function. So basically, what I need to do is I take the numerator, which is 10 over s squared plus 6s plus 15, and I divide by the same thing, 1 plus 10 over s squared plus 6s plus 15. Of course, you multiply by 1 is the same thing because h of s is 1. So it really means nothing, no modification to it. So you got to convert this to the same denominator. So how do you convert this to the same denominator? You just basically use the same denominator as the other one. So you got s squared plus 6s plus by 15 divide by itself, right? S squared plus 6s plus 15. So this is essentially equals to your 1, because the top and the bottom is the same, therefore it's 1, right? So now you have made what you have created is all the numerator and the denominator has the same function at the bottom, the denominator. So you can essentially cancel out all the denominator. You can cancel out all the denominator. And what you do is you write down all the numerator. So the top will be left with 10, and the bottom will be left with s squared plus by 6s plus by 15 plus 10, you get 25, right? So plus 25. So this is your closed loop transfer function. Now, the key thing about finding this, we want to look at this guy, the denominator, and this guy, the closed loop transfer function, the denominator. So we put them side by side, right? S squared plus 6s plus 25. That is for the closed loop transfer function, right? This is for closed loop transfer function. And then for the generic is s squared again, plus 2 zeta omega ns, right? Plus omega n squared. This is for generic. Now, of course, this term, needless to say, is equal, right? No problem. S squared and S squared is equal. So that one, no problem. So now you want to find omega n, you take the last one, right? But of course, in order for it to be equal, all terms must be equal. First thing, your S squared must equals to S squared first. If there is a number here, then you cannot equal, right? So you must divide first. You must normalize everything to S squared first. So now, for this term, we can see that omega n squared is equals to 25. So what is omega n? Omega n will be square root of 25, which give you 5 radian per second. Now for the second term here, 6s is equals to 2 zeta omega ns. S cancel away. So what you have, your zeta will be equals to zeta will be equals to 6 divided by 2 omega n, right? So 3 cancel with 2, then you have 3 over omega n. 3 over omega n is 3 divided by 5. Right? So your zeta is actually 0.6. Right? So with your zeta equals to 0.6 and omega n equals to 0.5, equals to 5, then you are ready to solve part 2, part 3, and part 4. Now, remember part 2, part 3, part 4, what do we need to find? Basically, it's a peak time, settling time, and maximum overshoot, right? So you need to find basically peak time for this case, TP. Second one is settling time. And the last one for 5%. And the last one is maximum percentage overshoot. So they want you to find percentage overshoot. Now these three equation can be found inside your equation, right? So let me see if I can share the equation right now to show you. Now, if I were to share the equation here, share. Now you can see percentage overshoot with your zeta, you can find. Now peak time is here, you can find, and the settling time for what? How many percent? Just now, what we say? For 5% criteria. So basically, 5% criteria will be this guy here. So use this formula. So with this, you are essentially able to solve all the question, right? Now, let me see if I can find the solution for. Let me see if I can find the solution derivation for just now the question that we left. Right? Just now the question that we left, we have not this guy. Let me stop sharing first, and then go to. Let me go to the lecture notes and let me pick the question, the lecture notes, and it's basically inside the lecture notes. Just now I said question 11 is inside the lecture notes. Let me show it to you before you may think that. Okay, so if you let me share it now to you. Let me share it now to you. Basically, in the lecture notes, okay, in the lecture notes, let me share it to you. Okay, if I share, this is basically your question 11. So they attempt to solve it, right? And you realize that if you use A1, A2, A0 situation, and you rearrange it, you basically get the expression, right? If you have any problem solving, do let me know. I will help you to solve. Okay, with that, we complete our this week lecture, right? With tutorial. So I wish you all the best, and thank you.